Hello everyone. This is the last topic of chapter 4, Fourier Transform Applications. In this topic, you will learn about the response of LTI system, LCCDE, modulation, and circuit analysis. Complex exponentials are the eigenfunctions of LTI systems. So this means that when a complex exponential is applied to an LTI system, the output is the same exponential scaled by the system frequency response at that frequency. So therefore, for a periodic input signal, okay, we are talking about the periodic input signal, the output yt equal to the corresponding input coefficients, which is xn, multiplied with the system frequency response, which is n. Do you know how to find the output signal of a Fourier transform? If you have the input signal and the frequency response in time domain, okay, xt and ht in time domain, your output signal will be in convolutions, which is xt convoluted with the ht. What if you have the input and the frequency response in the frequency domain? Your output y omega will be in multiplication. Okay, so therefore we can say that the convolution in time corresponds to the multiplication in frequency, which is one of the convolution properties of the Fourier transform. To find the output by t in a continuous time LTI system, instead of using convolution method, the output can be solved by finding the response in a frequency domain. After that, find the time domain response, which is the inverse Fourier transform, to get the yt.
Now let's look at the example. For a linear system with input xt and output yt, find the impulse response ht when xt equal to exponent power of negative t ut and yt equal to exponent negative t ut. Okay, so now for this question we can use the convolution properties. So y omega equal to x omega multiplied with hash omega. So this is the convolution properties. If we convert in the frequency domain, so we can use x omega multiplied with hash omega. Okay, so xt equal to, given xt equal to exponent power of negative t ut, then the x omega equal to 1 over 1 plus j omega. Whereas yt equal to exponent power of negative 2t, exponent power of negative 2t ut, then y omega we obtain 1 over 2 plus j omega. So from there we only have the x omega and y omega. Now we can find the hash omega. So hash omega is the y omega over x omega. So we substitute the value of y omega here to here, and then x omega, we substitute the value here. So we get j omega plus 1 divided by j omega plus 2. If you refer to the Fourier transform pair table, you won't find this kind of Fourier transform, okay, in the frequency domain. So we need to change the format. So how to change the format? So we can, if we look at the Fourier transform pair table, we can have either 1 plus a plus j omega or delta t. Okay, so we can use this one. Okay, so we just change the format. J omega plus 1 divided by j omega plus 2. So we can change to delta t by j omega plus 2 divided by j omega plus 2. So this one will contribute to delta t lah, because it's 1. Will contribute to 1. And then plus with, okay, denominator still remain j omega plus 2. Since this one is plus 2, so we need to minus 2 to remain the same value. And then this one is 1, we copy down, minus 2. After we simplify, we get 1 plus 1 minus 2. Now 1 minus 2, you get minus 1. So you get minus 1 over j omega plus 2. Okay, so from here we can find the hash omega. No, from the hash omega, okay, this one is hash omega, right? We can, from the hash omega, we can find the hash t by inverse Fourier transform. So inverse Fourier transform for this one, and then inverse Fourier transform of 1 plus j omega plus 2. So this will obtain delta t minus exponent power negative 2t ut. Okay? Now also we go to another example. This example is determine the convolution of xt equal to exponent power negative 2t ut and hash t equal to exponent power negative ut using Fourier transform. Okay, so again we use the convolution properties. We obtain y omega equal to x omega multiplied with hash omega. So given the input is xt and hash t, so we can directly. So you know that the xt will get x omega is 1 over 2 plus j omega, right? And then for this part, you will get hash omega equal to 1 over 6 plus j omega. So we can substitute in here. So 1 over 2 plus j omega multiply 1 over 6 plus j omega. So how? J omega. So we want to find out what is the value. So we can use the partial fraction. Use partial fraction. Okay, use the partial fraction expansions. And then we assume j omega equal to s. So to ease you to solve the questions. So y omega equal to, just now you get, okay, partial fraction. So you use a over s plus 2, then plus b over s plus 6. Okay, j omega we assume is s. So now we can find the a and b. Say we assume when s equal to minus 2, okay, so you get a. What is the a value when the s equal to minus 2? So a equal to s plus 2 no, we have this one. Okay, so to find a equal s plus 2 divided by s plus 2 and s plus 6. This one when s equal to negative 2. So what is the answer? So this one we can cancel out. So negative 2 plus 6, so it's negative 4. And negative 2 plus 6 is positive 4. Ah, Okay, so we have 1 over 4. Then when s equal to negative 6, so we can find the b. So b is s plus 6, s plus 2, s plus 6. So this one we will get negative 6 plus 2 is negative 4. So negative 1 over 4. So y omega equal to 1 over 4. A is 1 over 4. Then A 1 over j omega plus 2 lah. 1 over j omega plus 2. Then B is negative 1 over 4. Okay, then 1 over j omega plus 6. Okay, so we can, after this, you can find you can use the Fourier transform table, okay, to find the y omega, yt, sorry. So yt, so this is 1 over 4 is a constant. 1 over j omega plus 2, you can get exponent power of negative 2t. Then minus 1 over 4, this one is a constant again. 1 over j omega plus 6, again is the, from the pair table. So it's exponent power of negative 6t, ut. Alright. Okay.